to CS, oh, I don't have my mic. Right, sorry about that. All right, welcome to CS 3510. We're back from the break. L12B, I think, right? This is, the topic of today is constraint problems. We're going to prove more problems to be NP complete. Each lecture is like from a little interesting area. We did a lecture on logic problems. We did a lecture on graph problems. Today we're going to do a lecture on constraint problems, including knapsack. A constraint problem is you have perhaps a system of equations, and you're asked for a solution that obeys your constraints. You ask for something that satisfies some inequalities or equalities and so on. Subset sum, specifically, is such a constraint problem. We are asked for we're given a set of numbers and a target T, and we're asked, does there exist a subset S prime of S such that the sum of all the elements in S prime is equal to exactly this target T? Given a set of values, can you choose a set of the values so that you sum to exactly this target T, right? Yes?
You forgot to write the prime on S prime.
Oh, thank you. Thank you very much. Thank you. Yes. Can you choose a set of the items that sum to the target that you're given, right? Sometimes this is solvable in polynomial time because let's say the target is odd and you only have even numbers, right? So for example, let's say S is 2, 4, 8 and the target T is 7. Can't do it, right? Sometimes it's easy to determine if such a solution is possible, but not always, right? Now, if this was 6, this is good, right? So can you choose a selection of items that satisfy, in some sense, a single constraint? Does there exist a selection of those that equal this exact thing? And that's what subset sum is. Subset sum is NP complete. That should be a little surprising. Now, if we were asked another weird question, for example, what is the maximal amount we could sum to? Just choose all the items. So that's not a very interesting question. What if we were asked, could we sum to something less than T? This could also be done perhaps in a greedy way, right? But the question is, and this is part of the difficulty, we are asked to sum to a selection of items, a selection of values to exactly a target, exactly to T. That is quite difficult. And that's kind of what makes this problem NP complete. This problem should remind you of something. It's like a one equation version of knapsack, and we'll see that later today. But it is just a funnier knapsack. In fact, in interviews, they ask you to solve a variant of this problem where they ask not to sum to a target T, but they ask you to do something called set partition. Whereas you're given S, and you are asked to split it into L, R, such that they're disjoint, and that the sum, I'll use notation here, but the two have sum to the same thing, right? This is called set partition, and there's an obvious reduction from one to the other because you just consider problems of the form, right? Can you sum to something that's half of that? Fine. When they ask you this in an interview, the intention, what they're looking for is, can you implement knapsack from scratch to solve such a question? So there is a dynamic programming algorithm both for set partition and for subset sum that is basically the knapsack dynamic programming. It works exactly the same. Perhaps you could believe that you choose an I and then you go from I to WI, whatever, I to WJ for whatever item J, right? Same thing. But today we're not talking about that. We're talking not how to solve problems. We're talking about how to not solve problems. So we want to prove subset sum is NP complete. So it's a little finicky to think about because there's a lot of moving parts. Well, sometimes when you do such reductions, you have to translate from things to other things. And that can be quite difficult. Why? It was difficult for us to go from logic problems to graph problems because we had to convert a formula to a graph. Tricky. But then when you have a graph NP complete problems, you can convert those pretty easy. So we seek some kind of genesis transformation to convert, and I'll tell you it's going to be from 3-sat. Yes, 3-sat to subset sum. But how are we going to do this? We want, and like we mentioned with reducing 3-sat to independent set, local changes should map local changes, solutions should map to solutions. And in fact, preventing solutions should map to preventing solutions. So when we said, for example, x could be chosen if and only if the x was not chosen, right? So we say choose x if and only if, don't choose the negation of x. We simulated that on the graph, right? I'll just put independent set here, by connecting an edge between x and not x, right? So that's one important property that SAT appears to have that we would hope we can simulate by carefully crafting a selection of such items. That's the first part we need to consider. The second thing we need to do is ensure that every clause is satisfied. We did that in independent set by setting k equal to number of clauses. So it's not the case that you were asked about an independent set of size k minus 1, because that would correspond to a satisfying assignment of all but one clause, which is unsatisfying. That's not a satisfying assignment, right? So we kind of like simulated these two parts in the independent set graph that we constructed. We need to just think about how we can simulate both those parts in a selection of items that we're going to create, right? So we need to somehow encode a CNF into a selection of items. That's kind of what's going to become tricky about this. So what we can do is first craft the items in a way that's bitwise arithmetic. For each bit of the, first we create a number of items that correspond to whether each variable is true or false. Whether or not you select a literal to be true or on, right? We will craft these 6 items. Let's just suppose we have 6 items. We craft these 6 items in such a way that we cannot choose both. And we let the bits correspond to whether or not you can choose one or the other, right? Now, it must be the case not only that choosing one prevents you from choosing the other, but you must assign a variable. You cannot just say, I'm not choosing this one. So it must be chosen, right? One way we could prevent choice of both, let's say x and not x, is to have the target be 1 and have these both be 1, okay? If the target is 1 and these are both 1, you can't choose both of them. And in fact, to sum to the target, you must choose one of them. That's all we're going to generalize here. Let these all be 0. And instead, we want choices of, we'll interlock the choices of variables shortly. But right now, we want whether or not x is assigned and whether or not x being assigned means not x is not assigned to be independent of whether or not x1 is assigned, right? So what we do is we'll put the bits here in a separate column, like this. Oops, nope. Okay. Now, t here is not a 111, it's in binary. What is that, 7? Okay, so we set the items to be like this. Let's make sure we have this property. Notice that in order to choose items to sum to the value here, you must choose one of these two, one of these two, and one of these two. Now, for each of these, you can't choose both of these, you can't choose both of these, and you can't choose both of these. Okay. So we've started the first part of the quote-unquote simulation in the items, right? So these are, in correspondence, this would be like, what is that, 1, 2, 4. So 4, 4, 2, 2, 1, 1, and we ask for 7, right? So you must choose one of these, and one of these, and we must have a target be one of those, be that, right? So that's how we get the first part of it. Next, we need to interlock the clauses in the sense that every clause must be satisfied and no clause is unsatisfied. And there's a little problem we'll run into in that each clause may be satisfied in more than one way, right? So do we have any suggestions about how we can modify the current constructions of items and target so that we have we indicate when a clause is satisfied? example, let's suppose we have, I don't know, x1 or x2 not as a class. And let's say this is part of some larger CNF. Okay. What do we know about any satisfying assignment to such a CNF that contains this to clause? It must be the case that x1 is true or x2 is false. Correspondingly, we want either this item to be chosen or this item to be chosen. So how can we enforce one of those two items must be chosen? Yes?
Make another column with ones in those rows.
Now, I won't draw the dotted line, but let the C I column, let's just call the C1. We put ones in those rows, so we'll put a 1 here, a 1 here, and a 0 here, 0 here, 0 here, 0 here, and we could try to put a 1 there, okay? So what happens now is we add an additional row. First we add these rows just to ensure tranquility or whatever. And then we add another row for let's suppose we have one clause. So that you must choose x1 or not x2. There's a problem here though. What is it? Exactly. You can only choose one of them to sum to the target. If you choose both of them, you'll overflow. The whole thing is messed up. Let's come back to how to fix that later. But there is a fix we'll describe. So whatever this is, we just want this to be greater than 0. Strictly greater than 0, right? We don't know yet what it is, but it will be greater than 0, right? Now, if we could have multiple targets, that would be great, because then we can have it 1, 2, or 3, or whatever, right? But we can't. So I'll show you a hack around that. But for now, we do it that way, right? In specific, suppose I had the following CNF. I had x1 or x2 or x3, and not x1 or x2 or x3, and sorry, let's put this one and nope, let's do that one, and then we'll do x1 not or x2 not or x3. Okay. Analogously, what are our 3 clause rows going to be here? They're going to be like this. We're going to have clause 1, clause 2, and clause 3 are going to correspond to these columns. Now, for each one, we put a 1 in there if setting that literal to true turns on that clause. So, for example, this one would be 1, 0, 1, 0, 1, 0, right? C2 would be, this one would be a 1. That would be a 0. 1, 0, 0, 1. And then finally, C3 would be, correspond to what? 0, 1, 0, 1, 1, 0, right? So if the sum of that column exceeds 1, then we know that that clause correspondingly is satisfied, right? So every assignment corresponds to some subset of the vertices, some selection of the items. And we want to consider the satisfying assignments are ones that sum in the following way. Bitwise, there are ones here, and bitwise, whatever goes here exceeds 1, right? Forget carry for now, just suppose it exceeds 1. It's not 0. Whatever sums here is not 0. That means clause 1 is satisfied, clause 2 is satisfied, and so on, right? So this is the first part of our reduction. We have correctly, first off, do we agree? Any questions on the reduction so far, on the construction? Given a CNF, we can craft, in a very sneaky way, such a set of items, set of values that we encode the CNFs into bitwise, the clauses, right? Questions? Okay, now how do we agree to sum to more? How do we ensure that we sum to something more than 0? If we could choose multiple targets, maybe that could work, but we can't do that. So we know that this must either be a 1 let's forget carry for a second, okay? This could either be greater than 0. But because we're reducing from 3 sat, this is either a 1 or a 2 or a 3, right? Same thing here. Whatever it is, it's not 0. So what we can do is add dummy items such that choosing those dummy items will get you all the way to 3, right? What is 3 if not 1 plus 2? And if you already have 1 from your column sum, just add a 2 and then you're good. This is called the slack trick. It's not something you could be expected to come up with, but once you see it, it's pretty universal. So what I'm going to do is now just add a bunch of more random items. Let's call them, we'll call them slack 1. Let me double check this. We'll call it slack 1 prime, slack 2 prime, slack 3 prime, okay? And these are all going to be zeroed out in the first bits. And we set our target again to be 1, 1, 1, and then in these bits we'll set it to be 3, 3, 3. Let's not talk about carry for a second, just suppose that's what the column sums to, okay? What we can do now is we want this to be greater than 1, but we want it to sum to 3. So all we need to do is ensure that it's not 0. So what we do is we just have the slack variables help you do that. Right? Analogously, if, let's say, a plus b is less than or equal to some 3, then a plus b plus some slack is equal to 3 for s is equal to 1 or 2, right? The slack is there to make an inequality an equality. It just simply lets you talk about equality. So notice here, though, we need to sum to something that's 3, right? So what we could do is choose some number of items here, at most 3 of them, exactly 3 of them, in fact, that correspond to these 3, right? If a clause is satisfied by 1 literal being on, just choose S1 and S1 prime, for example. That'll be one of these ones plus these 2 will make this 3. If the clause is satisfied by 2, let's say X2 and X3 are on, then choose one of the slack items, and that'll sum that column to 3. Now, if all 3 are on, choose none of the slack items. So the slack can help you make the inequality. It can help you bring you up to an equality. Easy. Why doesn't this accidentally destroy everything, though? We just added a bunch of items that might, how do we know that that's still going to sum to the target? And the question is, can you choose a selection of perhaps only the slack items that sum to the target? Yeah. If you only choose slack items, for example, you cannot choose only S1 and S1 to help you sum to T2, to help you sum to T here, because you still need at least one of these 3, right? You can't get away with none of these, because you only have 2 1s here. You need at least 1 1 from one of these above, right? So that must sum to 3. There's no way around that this does not necessarily destroy the correctness of it, right? And the final question is, these are not numbers in binary. 3 is not binary. How do we fix this? Yeah.
Because 3 is 1, 1, you can just pad the columns with a 0 bit before the bit that you already have.
There's an easier way, though. That would work, I think, but there's a simpler explanation I'm looking for.
Do it in quaternaries?
Yeah, pretend everything's in base 4 instead of base 2. I don't even need to write that down. Just pretend everything's in base 4. So now this is not what would that be in binary? 1, 2, 4, 8, 16, 32. This would be 36 in binary. It's not binary now, it's base 4. So this would be 1, 4, 16, 16 plus, I don't know, forget it. But it doesn't matter. Whatever the items are in base 4, bitwise, they appear like this. Now, why do we choose base 4? I mean, it doesn't really matter, actually. Base 10 would work as well. But base 4 has the property that when we look at each column, none of the columns appear to sum to more than base 4, right? And no matter what we do, any correct selection of the items will overflow. Actually, maybe we can't do base 4. Here we have 5 ones. Suppose we then, it doesn't really matter. Let's just choose a base high enough such that it's greater than the maximum number of ones in any single column, right? So here is 5 ones, so it would be at least base 6. Here is, I see 5 ones, 5 ones. Yeah, it's always going to be 5 ones because there's going to be 3 above and then 2 slack variables. So let's pretend it's base 6. One of those cool things that doesn't really matter. Convert your CNF to a set of items bitwise in such a way. Pretend they're base 6, do all the math, and write that down. Your target is then also going to be in base 6 as 1, 1, 1, 3, 3, 3, whatever that happens to expand to. Either way, we've chosen it in such a way that there will never be any carry. So no column being oversatisfied, for example, accidentally rolls over and says something is satisfied when it shouldn't be, right? So this is the full kind of reduction. We just need to quickly write it down. But are there any questions so far on how to make this, right? Okay, let's quickly do the reduction. We claim that if phi is in 3 sat, then this selection of items, s comma t, constructed in such a way is in subset sum. Let's quickly prove it. If phi is in 3 sat, there is a satisfying assignment. For this assignment, choose the corresponding items. As in, if x, for each x1 being true or false, you choose that item corresponding to that variable being true or false. And then for the slacks, you just choose them so that they sum correctly to the column. This is then a subset which sums to target T. So we know that S comma T has a subset that sums to T, so this is in subset sum. Done. Proof is a little sparse. I'm just kind of waving my hands and saying obviously, but the whole 40 minutes I spent, not 40 minutes, whatever I spent, explaining how the things are made bitwise would actually be part of the formal proof, right, if we were to do this. But it's better to do it as an explanation than actually just say what the set of items are and then try to prove it, right? Do we understand that why the items do correctly simulate the formula? Right, we agree with that? Okay. Let's do the reverse direction. Now, should we do not P implies not Q, or should we do Q implies P? This is an open-ended question. And there's no right answer, but I just want to see if anyone has any guesses. Maybe for just demonstration purposes, because we did Q implies P so many times, let's just do not P implies not Q. If phi is not in 3 sat, we want to argue that there is no subset of items that can sum to the target T. If phi is not in 3 sat, then there is no satisfying assignment. Consider the items of S. For each, you cannot choose both xi and xi complement for any I. Otherwise, column-wise, that would not sum to t. So you can't choose both of those. So certainly, whatever the subset is, you must choose at least one of those. And for each of those, for any such subset, none have the last columns sum to 3, right? Why not? Yeah.
Because if it did all work out, then that would be a satisfying assignment.
Exactly. Otherwise, this would correspond to a satisfying assignment. So, S comma T as constructed cannot be in subset sum. Again, specific for this proof and not specific for what you'll do on like homeworks and stuff, this is a little sparse. Mostly because we spent so long waving our hands and everything that we said out loud and construction of the items bitwise should have been written down. Suppose I wrote all that down, that would be included as part of the proof, right? So what have we proven so far? We need one more thing. We're trying to prove that subset sum is NP hard. What are we missing? Yeah?
To prove that this reduction can be done in polynomial time.
Can it? Suppose you have n variables in your CNF. How long does it take to write down these items? Well, you have less clauses than variables. So let's say this is 2n plus 2n, right? So this is like 4n, okay. So that's the number of rows. How many columns are there? How many of these will there be? 1, 2, 3. 3 columns plus how many clauses are there? Yeah? Less than n. So this is like n plus something less than n. So this is approximately less than 4n times 2n, right? I'm saying the table of the number of bits is polynomial in the number of variables. So each bit doesn't take more than polynomial time to fill in, right? So certainly it's polynomial time to write down these items given your CNF, right? And then there's like an extra n to figure out what t is bitwise. The reduction then takes polynomial time. So mapping the specific CNF to the specific set of items in a target takes polynomial time. Okay? That is sufficient for us to conclude then that from 3-sat we may perform a polynomial time reduction to subset sum. So subset sum is at least harder than 3-sat. We need to now prove, yes? Oh, okay, sorry. We need to now prove subset sum is in NP. So, why is subset sum in NP? The verifier does what? It takes as input, let's say the items and an integer target t. What's our witness? Exactly. It's going to be the answers. Let's call it yeah, S1 to SK. What is the verifier going to do? Check S actually is a subset, and then check, fine, we'll say answer equals 0 for S in S prime, answer plus equals S, return answer equals t. What? In the number of items, yeah. Even if we're not in fixed point arithmetic, it's polynomial all around. So, polynomial. This is a polynomial time verifier. Given the actual subset, you can sum the items, obviously, and just check that it's tight t, right? So we've proven that subset sum is in NP, and we've also proven that it's NP hard. that's enough for us to conclude that subset sum is therefore NP complete. It is a new kind of problem. It's a constraint problem, and it is now elevated to the class of problems that are all as hard to solve as each other. These includes the graph problems, clique, vertex cover independent set. It also includes the logic problems, like SAT and 3SAT, right? Now we have a cool constraint problem we can work on. Let's use that to prove harder constraint problems are NP complete. Now, although the term reduction sounds like it sometimes is making things simpler, usually it's not actually. It's making things more complicated. But that's good because you can prove something more complicated by reducing from something simpler. So that actually makes the reduction simple, but it doesn't reduce anything. Knapsack is a harder thing than subset sum, certainly. So, but we can reduce from subset sum to knapsack. Right? First, we need a decision variant of knapsack. What is the search variant of knapsack, right? Describe to me how knapsack, what is knapsack?
Maximize the value while staying under a certain capacity.
What is the input to knapsack first?
A set of items with values and weights.
I'll do this. We'll say W1, V1 to Wn, Vn, right? And what else is given as part of the input to knapsack? Capacity W, okay? And we search for what?
Max value under capacity.
We'll say choose some, I don't know, I prime, subset of I, such that we maximize the sum of I don't know, what is it? The value Vi in I prime of Vi subject to the sum of the weights of the items we choose must be less than or equal to some W, right? We seek to maximize value up to some threshold. Important to note, especially in the next unit, these are both linear. There's no squares in them. That'll actually make things pretty simple. Knapsack and subset sum are both basically sums of things. As we'll see, that's kind of nice. This is a search problem, though, because we're seeking to maximize something. So how could I phrase this as a decision problem? Precisely. Let there be another parameter v such that we seek, can we steal at least this much given this constraint? That's what we ask. So the input to knapsack will be the set of items, encodings of the set of items, this integer w and this integer v, subject to, this whole part is just this stuff. All right. Fine, I'll write it. The sum for choose a subset I of the items such that if you sum the weights of the items in I, you're less than equal to W, but your value exceeds this capital V, right? The question is, given a capacity and a set of items, can you steal at least this much? That's how you decisionify a search problem, right? That's classically how it's done. And simply because you're seeking to maximize the amount you can steal, you would say, can I steal at least this much? If you're trying to minimize something, you might say, can I steal at most this much? Or can I steal less than this? You know? So it would be a less than or equal to. That's why it's a greater than equal there, because we're seeking to maximize. Okay, what's the reduction? Suppose, and this is going to be the simplest reduction we've done. Suppose I have my computable, polytype computable function take in s comma t, and I want to output an I, a w, and a v. What should my I, w, and v be? Yes?
S, for each S, the item should be, whatever that element is, repeated twice.
Mm-hmm.
And then W and V are both T.
set each item to be equal in capacity and weight. Sorry, value and weight. The value is equal to the weight for each item. We set W to T, and then we set the value threshold to T as well. Right? That's all it is. Why is that going to work? We'll see in a second in a proof. Before we do so, why is this in NP? Why is knapsack in NP? Yeah.
We get a subset of items and check whether it fulfills the conditions.
Yeah. Let's say our verifier takes as input I, W, and V. And what should our witness look like? You always want to decide what the witness is encoded as. What is the solution to this? In the search problem of knapsack, what is returned? Yeah. Not too complicated. So first you're going to check that all the items are actually items of the input. Then you check the two sums. This is a bit of an abusive notation because this is a set of items, but I'm asking about the value in the items. I should be asking about the value, the weight of an item in the set of items, but you understand what I'm saying, right? You check these two sums. How long does this take? Yeah. Sometimes you may encounter a reduction that actually does not take polynomial time. It's rare, though. The most obvious ones are polynomial. A non-polynomial time reduction may, for example, try to brute force search for a solution and then use that in the reduction. That's exactly what we do not allow and why we require a reduction to be polynomial time. Okay, that's the reduction. Let's just, well, that's the construction. First off, does the construction also take polynomial time to do? Why is that true? Yeah, setting W to T and V to T takes poly time. Setting, for each item, you add you double the item, and then you add it to the set of I. That takes, this is all linear stuff. It's just rewriting. It's pretty simple. Let's quickly prove it. Suppose S comma T is in subset sum. Consider the items chosen. Then there exists a subset S prime of S such that the sum of S prime is equal to some the target T here. Okay? Then the corresponding set of items, I prime, has the fact that I prime, the sum of vi in I prime of vi sums exactly to some t, which is equal to w, v, which is in fact greater than or equal to v, right? And it is also true that the sum of the values chosen in this item, the set of items, sums exactly to t, which is in fact equal to w, which is less than or equal to w. So trivially, because it's less than or equal to, because it's equal to, it's also less than or equal to, and also greater than or equal to. So we see then that this set of items has this knapsack instance has a selection of items that sum to whose weights sum below the capacity and whose value exceeds that threshold. That is sufficient for us to say that I, W, V is an element of knapsack. Fine. Let's do the other way. Suppose I, W, V is not an element of knapsack. Then for each subset I of the items, either the sum of the values is greater than one of the if it is not a solution in knapsack, then one of the constraints must be violated. Either the sum of the weights exceeds the capacity, or the sum of the values for that set of items is below the threshold, right? So if this is true, then the corresponding sum of items exceeds t. If the weight threshold is not satisfied, if you're overweight, then that specific subset sums to some number which exceeds the target. And if you're below your value threshold, then that also corresponding set of items must sum to something below the target. In both cases, we see if neither of the thresholds are met, if you either are overweight or below the threshold, that corresponding subset must either sum to some number above the target, or if the value threshold is not met, then that selection of items sums to something below the target. Either way, we know that the selection of items could never have a subset which sums to target t. So this cannot be in subset sum, QED. We have therefore proven that this set of items is in subset sum if and only if this set of items, this value, and this this value threshold and this capacity are in knapsack. Therefore, knapsack is NP complete. We gave a polytime verifier, we gave a polytime reduction, we proved the reduction was correct. So knapsack is a hard problem. We gave a dynamic programming algorithm for knapsack. It took exponential time. You can take this as evidence that you really can't do any better. If you could do better, you could probably do better. The reduction would translate. So then you could do better for subset sum. So you could do better for 3-sat. But you can't. So at least we don't think you can. Either way, this shows knapsack is a hard problem. Any questions? All right, constraint problems.